So today we're going to look at simulating matches, and in particular we're going to look at what I think is, you can say, is like the most important mathematical idea behind football, and that's the Poisson distribution. Last week we looked a lot at expected goals, and that's the thing you maybe read about the most as a sort of statistics applied to football. But I think what we're going to cover today, the Poisson distribution, is sort of more fundamental. If you like to think of the idea of mathematics underlying things, I think the Poisson distribution is the basic thing that underlies football. And you might not be familiar with the Poisson distribution. I'm definitely going to explain a lot about what it is today. But what it's related to is the memorylessness of football. Often when people talk about football, they talk about sort of the build-up of the game, how the game progressed over time and so on, and the sort of feelings and things that happened which sort of led to the picture of the match. That's valuable, but when you actually look at football from a mathematical perspective, you find that it really doesn't have that much memory. That goals can occur at any time during a football match, and they pretty much come at random. They come at random at different rates for different teams, which are better and worse than others, but they pretty much come at random throughout the match. There's a few kind of caveats about that, but that becomes our basic mathematical principle whenever we're modeling anything to do with football. It's the principle that we'll use today for simulating teams and matches, but it's also a principle that we'll use later when it comes to simulating match situations. The whole idea is that you can't see too far into the future in a football match, and that might seem that it makes it sort of random and difficult to predict, but actually the fact that we can't see too far into the future makes it more amenable to mathematics rather than less amenable to mathematics. Okay, so when are shots taken in a football match? This is one figure. Now I've actually forgotten which league it was. I think, is it the same as that one? Yeah, it is the same as that one. So it's the Premier League. This is the second half of the Premier League. And this is when what I've done is I've taken StatsBomb, I've taken the Y-Scout data, and I've basically put it into boxes from minute 0 up to minute 48 in Premier League matches for the second half. And I've measured how many shots occur within those minutes. And the main takeaway message here is, if you look at this line, this is the average number of shots throughout the whole match. I've cheated a little bit here. I haven't actually measured the length of all the matches. I've assumed that matches are on average 48 minutes long. If you really want to do this properly, you might want to make an adjustment for that. But this is the average number of shots per minute through, the total number of shots per minute that occurred in all of those matches. The average, of course, needs to be divided by the number of matches. And what you see is just sort of, for the main part, you just see a kind of fluctuation around this average. It isn't that there's 1 minute where all of the action happens. Maybe you can say that in the first minute of the match, in fact, you can say in the first minute of the second half, there's less likely to be shots. Second minute, maybe. But then after that, really up to the final whistle, there's equally likely to be shots in a football match. Now, I think that this is quite surprising when you haven't seen this statistic before, because we do tend to think, and I even think when I'm watching a match, that, well, there's going to be some sort of exciting chance. I have this friend who always talks about like the last big chance. And when we watch football together, he's sitting there waiting, anticipating what he believes is the last big chance that every team always has. And he always says that this will happen in the last 3 or 4 minutes. Then when he's happy, if it's his team who's losing and they need to have this last big chance, when he imagines that this big chance has occurred, maybe in the 46th minute, after that, he gives up all hope. But when you actually look at the stats, there really doesn't exist this last big chance. There is, throughout the match, a relatively even number of shots. apart from maybe in the first minute. Then you can also look at that for the first half and the second half. I was actually quite surprised because I've done this before and I haven't found this relationship, but I found that there does seem to be a slight difference between the first half and the second half. There are less shots in the first half than there are in the second half. And that might be, I think due to two reasons. One is that the matches start slowly. So in exactly this area here, we have, laser pointer on. In this area here, we have less shots. So when the match starts, the teams come out a bit slower. And then I think there tends to be more extra time in the second half than in the first half. So that's another part of the explanation. But the difference is reasonably small. In the first half, there's around about the same shots as there is in the second half. I think if you were a coach and you were trying to exploit something about this figure, this is what you would think this is what you should be thinking to exploit, because here it seems that there is some chance of getting more shots up. There is no reason, apart from the ball starts in the middle of the pitch, but it does that for a lot of the game. There's no reason that you can't start to have shots, certainly by the second minute in the game. But the overall thing I want to emphasize is that you have this, you could take the first and second half separately, but you have this reasonably, it's a normal distribution of the number of shots that you have per minute, and it's pretty constant throughout the match. And then when we look at goals, we actually find something similar. There are more goals in the first, in this particular data set. There were more goals in the second half than there were in the first half, but they come pretty much any time during a particular half. There's of course fluctuations here, and the fluctuations are bigger because the number of events is smaller, but there isn't really a clear pattern where there's an increase in number of goals coming as the match goes on, and neither is in the first half there's an increase in the number of goals. Again, maybe the first or second minute there's some pattern, but otherwise goals can come pretty much any time during a football match. Again, I want to emphasize that if you're working in betting and you want to find a small edge to exploit about this pattern, then there might be something for you to find there. But for nearly all other purposes of modeling football, it's the best assumption is to say that that goals come at any time during a football match. Okay, so I like to make this figure because I think it brings home the point. So if you divide a match into, let's say, 100 boxes, this is a 100-minute match, a bit longer than we might expect, but imagine you have a 100-minute match. And you say that one box is equal to 1 minute. What you're essentially doing is you're saying that goals occur more or less randomly during a match. And typically, a team scores 1.35 goals, just less than 1.5 goals per match. And you can think about, the way you think about this as a model is you basically think about just throwing these balls, these random goals, down at random inside the boxes. And sometimes you throw for a team, sometimes you throw one ball, sometimes you throw two balls, sometimes you throw three balls, but you'll basically throw these balls down randomly in the time slots, a bit like the time slots I had in the histogram. So you might have 2 goals coming into the match at random points. You might have 1 goal that you've dropped in at random. You might have 2 goals over here. And that's the basic idea of our model. We're dropping goals randomly into boxes. And then we can actually, from there, we can actually build a mathematical description of football. I was asked, for a documentary, I was asked to do this. I was asked to look at what are the chances of Bayern conceding 2 goals in injury time in 1999 in this famous match against Manchester United. I took a couple of statements from the commentators. I rewatched this match and listened to a couple of statements from the commentators. I really like this one. I tell you what, if they could equalize, and I'm not betting against them, I think they'll go on to win it, which I think actually goes against exactly what I've just said. You don't expect, if a team does get that random goal, there's no reason actually to believe more strongly that they'll get the next random goal, other than that they might be a slightly stronger team. And of course, it ends with nobody will ever win the European Cup final more dramatically than this, because Manchester United scored 2 goals in injury time. I'm going to say that they were within 1 minute. They were maybe within 1 minute of playing time, but they were actually within 2 minutes of each other. But for the sake of argument, we'll say that they were within 1 box of my model. And so basically, you can see the match like this. So this Champions League final, you can see the match as sort of a load of empty things, and then suddenly, pop, pop, 2 goals just occurred in the same box in the same minute of this match. And of course, this is very unlikely that they occur both in this way. But also, we watch a lot of football matches. We watch a lot of football matches where different things happen. And now and again, things like this will happen. So the fact that you get these 2 goals at the end of a Champions League final, it doesn't completely dismiss the idea that the goals occur at random. It just happened that in that particular match, it was bop, bop, both of the goals happened in this 99th minute. Again, I think I need to emphasize this over and over again, because it's a sort of fundamental thing about mathematical modeling. This is our assumption. It's not that I definitely believe that Manchester United only won the Champions League final because of randomness. It's just that it becomes a reasonable assumption, and very little that we observe in football contradicts that assumption. So for most cases, and even the Champions League final doesn't necessarily contradict that assumption. You can, of course, go in the other extreme. I did this because I thought it was fun. That both goals occur in the same minute or within a minute of playing time of each other. Well, the probability of that is 1 in 100, because I've got 100 boxes that they occur. And if they both occur at the same time, there's a 1 in 100 chance of that. And then that both occur in the second last minute, well, that's a 1 in a 10,000 chance, because you then specify specifically which minute you want to have. You can actually go a little bit further, and you can say, well, what if they actually both came from a corner? And then you start to get down to like, this is a 1 in a million chance. So this is a kind of opposite way of seeing it than I've just described, where we see it as random. We actually see what happened, and then we calculate the probability of that particular thing happening. I think I want to emphasize this is a just for fun calculation using probability. This, which we've looked at here, is the more serious model of how randomness can fool us in a way, or how we can control randomness. We see football matches as balls falling into boxes, and then we can actually manage to build up a model of those things. So yeah, 1 in a million that they chose. If you'd asked me before the match to calculate the probability that Manchester United would win with 2 corners within a minute or 2 of each other, I would have probably come up with 1 in a million. But given the amount of football that's played and the different things that can happen, all of those these different things happen. And I suppose it's the same with the Champions League, with the Liverpool come back from 3 goals down. Liverpool get 3 goals in the second half. A very unlikely event, but consistent with the idea that goals occur randomly in football. So often when we have these very strong stories about what happened in a football match, they often don't lie so far away from the randomness that we expect to occur in football matches. Fun calculation. Oh yeah, I forgot. I put that on there. It's the calculation based on if you asked me before the match, but of course after the match, this thing did happen. So it's no longer a 1 in a million chance. It actually happened. So the chance was 100%. But there is serious maths behind it. Oh yes, that we have this. We break things down into boxes, and we're going to put these balls down. And here is the serious maths then. So what's the probability of K goals occurring in a football match? Now, before I was looking at one team, and I said there was 1.35 goals. This number 2.7. Some leagues it's 2.5. Some leagues it's 2.8. It varies a bit, but I think in one Premier League that I was looking at, there was 2.7 goals scored in a match. And I'm going to assign them randomly between 95 minutes, which might be typical for a football match. I haven't looked at, neither of these numbers are absolutely cast in iron, but they're roughly what we see in typical football matches. Okay, so what is the probability of goals? Well, the way we work it out, and it's related to the box model, we drop, we see in each of these boxes, what's the probability that it's filled with a ball? So the probability that a particular box is filled with a ball is 2.7 divided by 95. So in this particular case, I've got 95 boxes, not the 100 I have here. And I say that each of them can be filled with a ball with 2.7. And this is this probability. So out of here, we're going to fill K of the boxes with a ball. And that's 2.7 divided by 95 is the probability that any one box is filled with a ball. And the probability that K boxes is filled with a ball is where you just multiply all of those together. But we also have to account for the boxes which aren't filled with balls. And that's 1 minus 2.7 divided by 95. So this is a probability that a particular box is empty. You see, the probability a box is empty is bigger, of course, than the probability it's occupied. And this 1 minus 2.7 over 95, well, that's going to be some reasonably large number. This number is about 1 in 30, something around this. So this is 29 over 30. And that's to the power of 95 minus K, because 95 minutes, and then we take minus K as the ones that are filled with the box. Then the last term we have to take, this is the combinatorial. So this is 95 factorial divided by K factorial times 95 minus K factorial. I should have written this out, but this is the factorial. What do you call it? This is the choose function, 95 choose K, which, just to say it again, 95 factorial divided by K factorial times 95 minus K factorial. And that then says, well, we have to choose each of these. So when I've dropped all of these balls into the boxes, I have to actually choose these things at random. And this is the binomial distribution, which is very typical, or is used to describe exactly this type of problem. You'll have seen it used, for example, you'll see. I'm not going to try another example. This is used for this type of problem of dropping balls in randomly. Okay, so I've had 95. I had 100 boxes here, and I had 95 boxes here. I decided on. Here's the question. So why have I divided the match into minutes? What's special about minutes? I could use 2 minutes. I could use 30 seconds. I could use 1 second. I could use 10 seconds. Why do I make my boxes minutes? And there is actually no good reason to make my boxes minutes, other than it's something that we understand very well. But we can actually think a little bit more about this question. And the question really here is, and I'm not going to give you a complete answer here, is how many seconds into the future can we predict a football match? Can we predict it 1 minute into the future? Can we predict it 10 seconds into the future? Can we predict it 1 second into the future? And that's basically the question of, can you predict when a goal will occur in this case? Because it's not just predicting anything about the football match, it's predicting that a goal will occur within 1 minute time frame into the future. Now, if you happen to believe that you can predict a football match more than 1 minute into the future, you can actually become extremely rich, because you've got time to place a bet on who's going to next score, and you'll become very, very rich because you'll be able to predict this. If you've got some sort of method of doing it, and that method is better than the bookmaker's method, which is based on the Poisson model I'm going to talk about, then you can get extremely rich. 10 seconds into the future, possible in some situations. It's possible when there's a penalty, for example. Then you can make better predictions that there'll be a goal in the near future if a penalty's just been awarded. But outside there being a penalty, it's pretty difficult actually to predict even 10 seconds into the future. 1 second into the future, I can kind of believe that it's possible to predict what's going to happen in a match. You've got a one-on-one situation. You can certainly get a much better than random estimate of if there's going to be a goal or not. But basically, this number here determines the number of boxes. So it should be somewhere, I think, between 1 minute and 1 second. So to get the number of boxes, you divide 90 or 95 or 100 or how many minutes you've assumed in your football match, you divide it by this time scale that you believe you can predict into the future. And I think that that's somewhere between 1 second and 1 minute. And that tells us, well, yeah, so I've said here 2.7 goals scored per match were randomly distributed between 95 minutes. But then we can rewrite this equation. We rewrite this equation by saying, well, whatever boxes you come up with here, if you think it's 10 seconds boxes, then it's 95 multiplied by 6 boxes that you should have. If you think that you really can't do it even on 1 second, then it's 95 times 60 boxes that you have. But we have these n boxes where 2.7 goals are scored per match randomly distributed between the n boxes. Again, we use the choose function here, n choose k. This is the probability that a goal occurs in a particular box. This is the probability that a goal doesn't occur in a particular box. We multiply these two together in the binomial distribution. And then we can do quite a nice thing. So there's a nice mathematical result that tells us this is sort of complicated to calculate, this binomial distribution. From a mathematical point, it's kind of unsatisfying that we have this massive n factorial thing here. And there's several reasons we don't want to use it, because a lot of mathematical machinery is not built up for dealing with these types of discrete distributions. But we can do the following thing. I'm going to go through this step by step, and you can have a look at this later. I've stolen this from a Math Caltech lecture, saved myself writing this out myself, but it's a very nice derivation of what's called Poisson's limit, or it's also called the law of small numbers, which goes from the from the binomial distribution here. This is exactly what we saw on the last page. And it goes to the Poisson distribution, which is shown here. And what we do is we take and start with the binomial distribution. This is where we expand it out in terms of the, this is what I should have done to make it clear. This is n factorial divided by n minus k factorial, gives n multiplied all the way down to n minus k plus 1. Then we divide by k factorial here. We have the mean mu here, which is 2.7 in our case. N is our number of boxes. But again, this is just the same form. So this is just a simplification here. Then what we can do is we can take this n to the power of k and we can divide through all of these terms by n. We've got a k factorial on the bottom. We've got mu to the power of k, and we've got this thing over here, 1 minus mu over n. That's just to the power of n minus k. That's the same thing as we had before. Simplify this thing again, or not necessarily simplify it, but turn it into something that we'll be able to deal with when we take a limit. So we're going to take a limit as we get n smaller and smaller. N bigger and bigger, because n bigger and bigger corresponds to more and more boxes. So more and more randomness in football. And we do this 1 minus 1 over n because what's going to be really nice here is that as the n goes to infinity, this will disappear. N goes to infinity, this will disappear. N goes to infinity, this will disappear. And we've got this k factorial under. We've left this because we also know what's going to happen when n goes to infinity. And then we do this, we put n goes to infinity in all of these. So we allow n to go to infinity. That's the number of boxes going to infinity. This corresponds to less and less predictableness in football. Now, of course, this isn't exactly true, because I admitted that on a 1 second interval, we can start to actually make predictions in football, but it's nearly true. To the n you get to, for example, 60 times 95 is pretty big. So in practice, this thing is going to work. When we let n go to infinity, all of these terms become 1. This term becomes 1. This term becomes 1. This term becomes 1. Over 1 here. K factorial is not affected by n going to infinity. Mu to the k is not affected by n going to infinity. This thing here, well, you've got mu divided by n goes to infinity, so this thing just goes to 1. And then this last part here, this is probably the harder one to work through, but actually this is by definition, the limit of this is e to the minus mu, as you have 1 minus mu divided by n to the power of n. So you get e to the minus mu. And so finally, you're left with Poisson's distribution, which gives you the probability, that gives you this probability of scoring in terms of your original parameter, mu 2.7, k, and you'll see that n has disappeared, which is very nice. So we don't need to think about our boxes anymore. Provided we can write our football game in terms of enough boxes, we get the limit we want, which is a lovely result discovered by Poisson many, many years ago, and is also known as the law of small numbers, which I think is a lovely thing. And the small numbers is the small number of goals in football. There is a small number of goals in football, and that allows us to make this a derivation of the Poisson distribution. And what does this mean in practice? Well, I told you this equation for 95 minutes, then I looked at this equation for n. And in practice, this means that this equation, the number of goals in your match, will be described very well by this equation, 2.7 to the power of k, e to the minus 2.7 divided by k factorial will give you the probability you'll have a particular number of goals in the match. This is really a kind of, this is a bit geeky actually, or what can I say about this? I actually thought about this a lot, that 2.71 is actually very close to the number e. So e is approximated by 2.71. So the fact that you have 2.7 goals in football means you can actually write this equation down, which will work very nicely for a lot of goals in football. And you see that this isn't actually a parameter-free equation, because e isn't a proper parameter in maths. E is a universal constant. So you can write down the number of goals in football just using universal constants and k, which is the thing that you want to estimate, is the number of goals. So e to the k to e to the minus e divided by k factorial, no parameters whatsoever, will give you a fundamental model of football. I think that this is, I am joking a bit here, but this is sort of as fundamental as gravitational models or quantum theory models. This is the fundamental equation of football, where you don't have to, you don't have any constants whatsoever in describing the number of goals that occur in a football match. But I do want to be clear that that is also because of the coincidence that it happens that 2.7 goals on average are scored during football matches, I think. This is probability, proportion of matches with a particular number of goals. We've got the Poisson curve here. You can do this yourself for the 10 goals per game. We've got the Poisson distribution there. We've got the data here. And it's not a perfect fit, but it's very close to how many goals you get. There's one match here which is overestimated. 1-0 seem to be overestimated in La Liga. If we look at Bundesliga, possibly overrepresented 1-1s here. It's overrepresented 1-0s here than predicted. Maybe overrepresented 1-1s in Bundesliga, for example, more draws than we might expect. You can see 0-0, more draws than we might expect, less 1-0 results, but pretty much consistent with the Poisson model. I think the last thing I want to say before I go over to, because what I'm going to do next is like how we're going to use this. One thing I want to do last here before we I go and have a look at your questions and we go into the break is that the Poisson distribution is fundamental to football. If you're interested in basketball or a lot of other sports, then it's actually the normal distribution, which is the fundamental distribution. And the reason is this is actually the opposite of the, well, not the opposite of the law of large numbers, but we have the law of small numbers for things that don't occur very much, which is goals in football. For things that occur a lot, we have the law of large numbers, and that's where the normal distribution comes in. Normal distribution is what you get if you add up loads and loads of random things. So if you add up loads and loads of random scoring in basketball matches, you get a normal distribution. And I made this actually one for my latest book. I looked at basketball and found very nicely and regularly for NBA games 2018-19, and I'm sure you can do this for other seasons, you have the normal curve, this bell-shaped curve, very accurately describes the number of points scored per team in each game. And that's because you can see basketball is the sum of lots and lots of random events, while football is the sum of very few random events. Law of large numbers gives you the normal distribution. Law of small numbers gives you the Poisson distribution.